All right, let's jump right in. We are about to tackle a problem that seems, well, completely impossible, and yet our modern world depends on solving it every single day. We're going to talk about how we unblur reality itself.
You know that feeling, right? You take what you think is going to be the perfect shot, but you look at it and it's just a little bit blurry. You've got the fuzzy result, but you know the sharp, perfect original is hidden in there somewhere. Well, it turns out that getting it back is one of the great challenges in both science and mathematics.
Okay, so here's the heart of the problem. You start with a perfect image. Let's call it F. It passes through some kind of system A. That could be your camera lens, the atmosphere, anything that causes blur. Then a little bit of random noise, N, gets added into the mix. And what you're left with is G, the blurry image you actually see. Now here's the thing. We have G, the final product, but what we really want is to find F, the original. This whole process of working backward, from the effect to the cause, has a special name. It's called an inverse problem.
So how do you solve an inverse problem? Well, it's not really like doing a simple math equation. It's actually a lot more like being a detective. We have to solve the mystery of the missing cause.
Think about it like this. A direct problem is easy. If you know the cause, say the sharp image, you can pretty easily predict the effect, the blur. But an inverse problem completely flips that script. We have the effect, the blurry data, and we have to figure out the cause. It's like we've shown up at the crime scene, and now we have to find the culprit.
You know, the great detective Sherlock Holmes himself absolutely nailed it. Thinking synthetically, from cause to effect, that's common. But thinking analytically, working your way backward from the clues to the solution, that is a rare and incredibly powerful skill. And that's exactly what we have to do here. We have to become data detectives.
But if it's just a matter of working backward, why is it so ridiculously hard? Well, it turns out our little mystery has a major complication.
The reason it's so tough is that these are what mathematicians call ill-posed problems. See, a proper, well-posed problem has to meet three conditions. A solution has to exist, it has to be the only solution, and it needs to be stable. Inverse problems? Oh, they often fail on all three counts, spectacularly.
And this right here shows the core of the issue perfectly. On the left, in what we'll call the object space, you can have two totally different original things, but after they pass through that blurring process, they can end up looking like the exact same blurry image on the right. The process is leaky. It just loses all the fine details that made those two objects different in the first place.
So let's just break down those three big challenges. First, like we just saw, information is lost. That means there might not be one single unique answer. Lots of different original images could have made our one blurry photo. Second, real-world measurements always have noise. That random static might mean that a mathematically perfect original just doesn't even exist. And third, and this is the big one, instability. This right here is the real killer, instability. If you just try to reverse the math, the process acts like a massive amplifier for all that noise. Even the tiniest, most insignificant error gets magnified 1,000 times over, completely destroying any hope of seeing the original image. You're just left with a mess of static. A direct reversal is, well, it's impossible.
So it really seems like the door is slammed shut, right? We can't go backward. But a brilliant shift in thinking changed everything, and it gave us a kind of golden rule for solving the unsolvable.
I mean, this is the question that scientists and mathematicians were stuck on for decades. If a perfect, mathematically pure solution is completely off the table, what's next? Do we just give up?
Nope. We changed the question, and this is the breakthrough, the golden rule. Stop demanding the one perfect true answer. Instead, we search for approximate solutions that also happen to satisfy extra constraints, rules that we already know are true about the real world. And this is a huge philosophical shift. We stop asking, what is the perfect mathematical inverse, and we start asking, of all the millions of images that could have created this blur, which one is the most physically plausible? We're not just doing math anymore. We're using real-world logic to guide us to the best possible answer. So what do these real-world clues actually look like? Well, a lot of the time it's just common sense. We know the original object is probably smooth, not full of random static. We know there's a limit to how bright it can be. And we definitely know you can't have negative light, right? This whole process of adding smart constraints to guide the solution, it has a name. It's called regularization. It's how we weed out all the absurd possibilities to find an answer that actually makes sense.
Now, I know this might all seem a little abstract, but this breakthrough in thinking has a payoff that has fundamentally changed our world. It's allowed us to see things that were once completely, totally invisible.
And the impact of this way of thinking is just staggering. I mean, every single technology you see here relies on solving an ill-posed inverse problem. From the sharpest images of distant galaxies to the medical scans that can literally see inside our own bodies, none of it would be possible without this breakthrough.
You know, take a CT scanner. Its raw data isn't a picture at all. It's just a whole bunch of shadow measurements from different angles. Or think about the Hubble telescope, which was famously launched with a flawed, blurry mirror. In both of those cases, scientists used regularization, adding rules from physics to transform that messy, blurry data into the stunning, crystal-clear images we all know today.
Okay, so let's sharpen the focus one last time and bring this whole thing together.
The big takeaway here, the most crucial point, is a really powerful strategy for solving problems. When a direct, perfect solution is impossible because of lost information and noise, the way forward is to change the rules. We find the best possible answer by adding smart, real-world constraints that guide us away from absurdity and toward a plausible reality.
This way of thinking lets us de-blur images from across the cosmos and from deep inside our own bodies. So it really makes you wonder, what's the next great blurry picture we need to solve? What's the biggest ill-posed problem? In physics, in biology, or maybe even in consciousness itself, that we're still trying to sharpen into focus. Thanks for joining this explainer.